The BSides DC 2017 videos are brought to you by Threat Quotient, introducing the industry's first threat intelligence platform designed to enable threat operations and management, and Data Tribe, a new kind of startup studio co-building the next generation of commercial cybersecurity, analytics, and big data product companies.
My name is Khaled Al-Hassani. Detecting malicious SSL certificates using machine learning. I know on the schedule it says in your spare time. I haven't included that here. I'll get to that a little later. But it's kind of an accurate statement. So the motivation is pretty much well known by now, that increasing share of encrypted network traffic, let's say half or more than half of the network traffic is encrypted. And there is a push to monitor the traffic for malware and other threats without man in the middle, meaning without decryption. And the SSL certificate provides us with a fundamental part of the encrypted traffic metadata. And it provides us with its information that we can use. So as with any machine learning or data science project, first you need the data. And in this case, we need labeled data, meaning we need certificates that we know are bad, certificates we know are good, more or less good. We know there can be some certificates that we know they're benign, they turn out to be malicious, but in general, benign certificates and malicious certificates. Collecting benign certificates is not a big problem. There are many available. We use the source census, plenty of millions of certificates there. We collect the trusted certificates there. We sample from there. Alexa 10,000 domains, we sample from there. And trusted certificate authority root certificates. These are self-signed, like a few hundred of them. Getting the malicious certificates is a more challenging problem. And this is done by our threat research team, particularly Jason Reeves. Basically collect the data, the IOC data of different malwares. Okay. Collect IOC data of different malwares, and for the ones that use SSL, we store this data, and for the ones that use SSL, go back and scan this data, meaning port, IPs, and pull out the certificate. For this study, so far we have a data set of about 13,200 certs, including 4,300 roughly malicious certs and around 9,000 benign certs. We want to keep the data set from being too imbalanced. We can collect millions of benign certificates, but that wouldn't be very helpful because we don't want to get the data set to be too imbalanced. If we look at a sample parse cert, some of the fields there, serial number, begin date, which is the issuing date, in this case 2014, end date, meaning expiry date, in this case 2026. Subject fields include the country, US, the state, locality, organization name, email address, common name, and in this case, there is some unstructured name that's there. It's not usually there. The issuer, in this case, we only have one field. It's organization. The key length, key type, the signature algorithm. In general, there can be more fields for the issuer, including all these fields. So far, it doesn't look very bad. Some names that don't look terrible. If you look at the dates, the issuing and end dates, this is a large time span. And this is usually uncommon for regular certs. It can be common for root certs, but this, like certificate authority root certs, this is not a root cert. So there is something, might be malicious. Another important thing in certs is extensions. And these are additional fields that can be present in a cert. I'm going to zoom in on the extensions here. So the ones that are present in this certs are basic constraints, include CA flag. Is this a certificate authority? There can be another field called path length, meaning how many certs can be authorized in a chain. The field 0 here means that these extensions are not critical. So each extension can be critical or not critical. Key usage. In this case, it has three entries for key usage. Extended key usage. This is relevant mostly for leaf certificates. And subject alt name. In this case, it has a DNS, this DNS. So other extensions can be present in addition to the ones that we see in this certificate, including issuer alt name, subject alt name, authority key identifier, certificate policies, and so on. As I mentioned, each extension can be critical or not critical. I'm going to talk a little bit about the machine learning classification algorithms that we use. So the basic idea is we want to build a model, train a model using the data, using some algorithm. And after all that, we give it a certificate. It will tell us if it's malicious or not. So we use these algorithms, well-known algorithms for classification: random forest, logistic regression, support vector machine. And at any point in this work, we can switch between the algorithms. We're not really committed to any of them. However, we compared the accuracy, and in this case, the performance we mostly care about is the false positive rate. And of the three, using the same data sets. And the random forest, in this case, gives us a better false positive rate, lower false positive rate. So 0.3%. I'll get into the details later. 0.3% compared to 0.5% for logistic regression and 0.7% for support vector machines. In addition, and this is important, so in addition to the data set that we use for training, the labeled data set, we want to test how the classifier does in the wild. So we collect data from some network, and we test it on that network. So real network, not related at all to the training data. And we test the algorithm there to check the sanity, because it might work for the data set that we have, but then when we put it in the wild, it might go crazy and gives a lot of alerts. So for the rest of the presentation, I'm going to be using random forest. So a few words about random forest. It's an ensemble of decision trees. So what's a decision tree? This is an example of a decision tree that I got on a cartoon that I got from Wikipedia. Unfortunately, it's not a happy one. It's a classification for passengers, whether they survived or they didn't survive the Titanic. So not exactly happy. And it goes like this. Is the passenger a male? If no, you have a high probability of surviving, 0.73, 73% chance of surviving. If yes, you go down. You look at another feature or another property of the passenger, and the age. Sorry, I can see. So, is the age greater than 9.5? If yes, then you have a very high chance of not surviving here. If yes, if no, then you go down furthermore. You need more information. You look at another attribute or another property. And in this case, it's a number of family members. And you go yes or no. So this is a decision tree. Now you want to build the decision tree. So you want to determine what features you look at and what features you decide on, and the split. And this is done using information gain. So first you look at the feature that gives you the highest information gain from the split, which is in this case the gender, and you go down. By the end of the training, you build multiple trees, and then which gives you your random forest, which is an ensemble of trees. So that's by the end of the training. And then you have a new certificate. You pass it through all these trees, and the decision, you look at the decision of each tree, and you look at the average, and it tells you if it's malicious or not. We use widely used, well-known scikit-learn Python library, and these calculations are not highly demanding. I do that on my laptop. So that's part of why we say in your spare time. It's not highly demanding. I'm gonna get into the core of the work and look at the results. The first step is we have the certificate, we have the attributes. What do you use from these attributes? We can't just give the certificate as it is. So we want to obtain or extract information in some form or some representation of these attributes. So we have these general guidelines or general options. A general feature, let's say issuer country. We have these options. We can use just the value as it is. Issuer country is the US, for example, or present or absent. There is no issuer country. This can be another way to encode this. Length of a string value. This is useful in the case of the serial number, because the serial number by itself doesn't really mean much. So the extensions are similar, whether they're, one option is just to look if the extension is present or absent. Critical or not critical. For some extensions, we dig deeper and we look at the values. Most extensions have multiple values, so we dig deeper and we look at the specific values. And for some extensions, we look at the number of values, number of subject alt names, number of issuer alt names, and so on. Can I get here into this feature extraction from attributes into some detail? And this is basically the bulk of the work. The algorithms are well known, are well established, and the bulk of the work are actually two parts: obtaining the malicious certificates and doing the feature extraction. The serial number, we use the length of the serial number. The value of the serial number doesn't mean much. If two serial numbers are close, then that doesn't mean that there is similarity. We use the length of the serial number basically because there's a correlation between the certificate authority and the pattern between the length of the serial number. So there's some information there. Issuing and end dates, how do we use that? We use the validity period in years. Like the certificate we saw, it has a validity period of 12. So that's the feature 12. And whether it's expired or not. The version of the certificate can be 2, 3, etc. We use the value of the version. The key length, it has specific values, 2048 and so on. So we use the value itself. Key type, similarly, signature algorithm, we use the value itself. Extensions, the whole set. As a set, we use the number of extensions and which extensions are, or whether there are extensions or not. There is some redundancy here, but the main idea is to use the number of extensions. Each of the extensions, the encoding takes 3 different values. If it's absent, the extension is not there, present and critical, and present are not critical. So it can take 3 values for each of the extensions. We dig, for some extensions, this is a general one. For some extensions, we dig deeper. We look at the number of subject alt names. We look at the number of issuer alt names. Key usage has a specific set of values, and any of these values can be present or absent. So we look at each value, like, for example, digital signature. So if it's there, it takes a value 1. If it's not there, it takes a value 0. other values in cipher only, and so on. I think there is a set of 9 values there. Extended key usage similarly, similar to that. Authority key identifier, we use the value as it is, because in principle there is a limited number of certificate authorities, so the value set is not overwhelming. So we can use the value in principle. The subject and issuer fields. The issuer country, we use the value as it is. So US, Japan, China, etc. Whether it's valid or not. This is another feature. We see sometimes values like XX, dash, dash, and so on. These are not valid countries, so we use that as a feature as well. For all other issuer fields, we use the values, because there is it's a more restricted set of fields than the subject values. For the subject values, we use the country similarly to the issuer country value and whether it's valid or not. The other fields, because there is a large set, so it can be anything, anywhere. We use the values of the encoding is if it's absent or present, so 0 or 1. Now, all this are we're still not ready to give to the machine learning algorithm. We have to do a little more encoding. So this is a small set. Let's say you have a small data set, for training set, and you collect the values, and this is basically the feature space that you end up with. So you have some certificates with issuer country China, US, Japan, some certificates with version 2, version 3, length of serial number 3, 7. Some certificates have key usage is critical. Some have this value digital signature and key usage, and so on. So this is a small subset. If we look at one of these certificates, it will be a vector of zeros and 1. In this case, the certificate has issuer country US, it has version 3, it has 7 as the length of the serial number, and so on. So we take this numerical vector, zeros and ones, and we feed it to the machine learning algorithm that we train, and it will tell us if it's malicious or not. So basically, this is the well-known machine learning pipeline, with details related to our work on certificates. Now we start looking at some results. What we're mainly concerned with are 2 false positive and false negative rates, with more emphasis on false positive rates. And I'll explain why. So as I mentioned before, the data set has 13,000 that we use here. It has 13,200 certs in the data set. And we do the train test split, 80-20, meaning we sample 80% of these certificates. We use that as our training data set. We train the model. And then we use the remaining 20% of the certs for testing. We look at these 2 measures. The false positive rate, meaning the ones that the classifier says they are positive, they are malicious. Out of the number that we have that are negative, they are benign, meaning that it classified them as wrongly as positive. And this here, the number of the negative is the ones that are truly classified as negative, true negative, and the ones that are classified as positive. For the false negative rate is very similar, but the mirror image, meaning the number of certificates that were classified as negative, meaning benign, over the total number of positive certs. So we value. This is random forest, and it gives us a probability. And we vary the probability threshold. Like where do we set the threshold where we decide it's malicious or not? Meaning, So if we increase this probability threshold from 0.5 to 0.9, meaning that we want to be more sure that the certificate is malicious. The false positive rate, as expected, will decrease from 0.3%, so this is multiplied by 100, and this is percentage, so 0.3% to 0.1%. The false negative rate will increase as we increase this, because we want to be more sure, so we miss some certificates that are look malicious, but they don't look very malicious. The probability is, let's say, 0.5, 0.6, so we miss these, and the false negative rate increases. So this trade-off is there, and you have to decide which one you care about more. In our case, we care about the false positive rate because there is a large number of benign certificates. And if the false positive rate is high, it will give you a lot of warnings or a lot of malicious certificates that are not actually malicious. So you will be overwhelmed by the number. So these are the numbers we get: 0.1%, 5%, and I'm going to say a few words what that means. 0.1% means that false positive rate means that if you have 1,000 benign certs, you will get one cert the classifier will tell you out of these 1,000 benign certs to 12, it will tell you that this is malicious out of 1,000. So for that, you will miss, in return, 5% means, or 5.5% means that out of 100 malicious certs, you will miss 5 or 6. It will tell you it's not been malicious. So this is what the numbers mean, and this is a trade-off. As I mentioned before, it's very important that we test this on independent, real data we collect from the field. Make sure that these results are not just a property of the data set that we have, and the classifier works well in the field. So now the dependence of how do these results depend on the data set size? Why we look at that? Because as I mentioned, the number of malicious certs that we have is an issue. We're bottlenecked on that. We want to make sure that this doesn't hurt us. Here I'm plotting the false positive rate. I'm false positive rate as a number of certificates in the data set. So these numbers, 2,000, 4,000, etc. We sample them from the big data set, which is 13,000 certs. We sample many times. For each sampling, we do the test data split also many times. We calculate the false positive rate, and we calculate the average, and we get this result. And this is a probability threshold of 0.5 that we saw before. In that table, it was the false positive rate was around 0.3%. So at the beginning, for a small data set, the false positive rate is high, and it decreases, and it saturates. Let's say if you fit this to a plot, it will saturate around 6,000 to 8,000 here, and plateaus. So meaning that we have a good number of certs for training. Now, with that said, we continue to harvest malicious certs. We're not stopping here. And why? Because if we want to squeeze out more accuracy, a lower false positive rate, we can still look at more data. We can still do more feature engineering. We can look at other, let's say, more complex methods, meaning deep neural networks, and see if this trend changes. If it keeps decreasing with the data set size. So, meaning we can still gain from from collecting more data. And also, we can still gain by making the classifier work better in the field. The final set of results I'm going to show is the feature importance. We looked at the attributes and how we extract features from them. We used a bunch of them, and we want to get some intuition as to which of these features, which of these attributes is more important in determining whether a certificate is malicious or not. So this is the table for the most important features. This is the feature importance percentage. This is what we get from the random forest classifier. What I'm showing here are the features that have importance higher than 1%. So this is the last one here. Other features have importance lower than 1%. And these all add up to around 93%. So this is the bulk. If we look at these features. So certificate policies. This is an extension. Apparently has the highest importance. Authority info access. This usually has links to the certificate authority URLs. Certificate policies has also links to specific policies related to certificate authorities or PKIs and so on. Subject alt names, like different names for a website and so on. This is TLS web server authentication and extended key usage. Critical key usage, meaning if the key usage is critical or not. Authority key identifier, this is an ID for the certificate authority, and etc. It goes down. One here is the issuer country, if it's valid or not. And then here it's the issuer country, the value of the issuer country, the organization in the issuer entity, and so on, length of serial number and so on. And what we see here is that extensions have a particularly high importance, and in addition to issuer fields. So you cannot get away without looking at these attributes. Also, I want to point out here that there is a lot of randomness. It's a random forest, there is sampling, and so on. So you might run another set of calculations, sampling and averaging, and so on. And you might not get this exact order or these exact numbers. But the most important ones will be there. So this might be instead of the third place, it will be the second, and so on. But the most important attributes are going to be there. So the order might change a little bit. Now, I'm going to take the first 5 attributes and look at them in a little more detail. So I look at the prevalence of these attributes in benign certs and in malicious certs. Basically, the idea is to get some intuition as to what a malicious cert looks like, what to expect, and what a benign cert looks like. So certificate policies has the highest importance, and it turns out that it's present in this extension, certificate policies, is present in 95.89% of the benign certs, while it's present in only 9.75% of the malicious certs. Authority info access, same thing, very similar numbers. Subject alt name, again, similar numbers. This is subject alt name, meaning whether it's present or not. It has a little bit higher presence in malicious certs than the other two. Critical key usage, it's mostly in benign. It's mostly absent in malicious. Authority key identifier, similar story, except that it's a little more prevalent in malicious certs, which is most likely why it gets lower importance than the above attributes. We go back to the sample cert that I saw at the beginning, and we look at the extensions, since we saw that the extensions have a particularly high importance. And these are the the attributes, or from the extensions, the features that have high importance, and we look at them in this cert. Certificate policies, it's not present here. It should be present, usually. Authority info access, not present. Subject alt name, it's present. TLS, web server authentication, it's there. Critical key usage, the key usage here is not critical. And the authority key identifier, it's not present here. So we have some bad features. It's on the wrong side of the feature split, the cert. Some that are okay, and 2 that are okay. And here it turns out that this is actually a malicious cert. So. Now, finally, this are the summary and conclusions of this work. So we applied machine learning, I would say, successfully to classify SSL certificates. We calculated the feature importance and prevalence, and this gives us a good intuition as to, looking at a certificate, kind of guessing whether it's good or bad. It's not exact, so usually, sometimes you can see a lot of these features that look good, but there are other features, and it ends up, other features, and ends up being bad. So, but you get a good intuition. Studied the effect of the data size, being limited by the number of malicious certs. We studied that, and we see that it doesn't really hurt us. Some future direction. Obviously, we're going to keep collecting malicious certs. Dig deeper into features. Try to squeeze out more higher accuracy. Again, in the spirit of looking for higher accuracy, we look into whether this will help us using more sophisticated algorithms, mainly deep neural networks, which is very trendy now. Also look at the certs in a broader context. We looked in this study, so far we've been looking at the certificate itself. We can look in a broader context, meaning the certification chain, the parent, child, and so on. More metadata from the TLS traffic, and so on. So with that, thank you. This work has been done by myself and Abhishek Sharma at the data analytics team at Fidelis, by Jason Reeves at the threat research team. He has this project of collecting the malicious certs. And we are hiring, so if you're interested, please talk to me or to Daniel with the Fidelis t-shirt. And you can look at the Fidelis security website. All right, thank you.
So your benign set is kind of biased towards the most popular sites because it's the Alexa top sites. Do you find that your model still works with far less popular but still benign sites that might have sketchier, less hygiene?
Yes. Actually, it's not only the Alexa 10,000. We use the Alexa 10,000. We sample from that. We also have the census. And there, it's not necessarily, we sample from that. It has millions of certificates. We sample from those. That is not necessarily the most popular. Now, well, it has, it has flags whether these certs are trusted or not. Again, it can be trusted and malicious, but we're relying on the fact that the percentage of malicious certificates out there among trusted certificates is low. So there might be a little bit of mislabeling, but thank you.
I assume you've actually set something up to test for the responsiveness or attacking this in real life.
Yes.
What's your actual response time? Are you talking about seconds, minutes, hours at this point with this particular classifier?
Oh, no, it's definitely not hours, not minutes. It's close to real time.
Repeat the question.
So the response time in real life, meaning out there on the network, you're collecting the certificates, you want to classify them, and how fast is that, right?
We're talking about 100 milliseconds, we're talking a second.
We haven't gotten into that detail yet. Well, we're working on putting that in we're working on putting that in the product. We have a database. We collect from these certificates from the data from the field, and looking at one certificate is extremely fast. I don't think it's anywhere near a second. So
Just asking because
yeah,
there's a lot of packets coming through.
true.
With false positive rate, have you looked at training it on specific sets of malicious certificates in order to lower that false positive rate rather than just all malicious certificates as a full set?
Specific types of malware. We haven't looked at that. One reason we haven't looked at, so the malicious set of certificates. Have we looked at specific? Have we partitioned the set into different malware types, different actors, and so on? We haven't looked at that yet. One reason we haven't looked at that is that we don't have a large data set. So if you partition it farther, the training is not going to be good enough. Yes.
How about false negatives, considering a lot of people are using this kind of algorithm to bypass and to be able to compromise based on tricking the algorithm into allowing them in? Are you looking at the false negative side too, so at least you can see people toying with that?
Yes. So I think there is some work towards tweaking some certificates that look benign, and making the classifier, or fooling the classifier, basically. This is something I haven't mentioned here, but this is something that we're going to be working on.
Is there a feature that you think would have an impact that's not like in what you get from the certificate authority and you wish you had?
A feature that is not present in the certificate itself. I don't have one. When as I mentioned, we're going to look at the broader context. I'm sure we'll get something there. Thank you. Yes.
Is your intent to use this as a real-time alerting platform, local stuff going across the wire, as a retroactive platform, or what is your long-term, what do you expect the value on?
So it's like this. We have the sensor. In our product, we have multiple components. One of them is the sensor. Is the one that looks at the wire, and this is the one that collects the metadata. It collects also certificates as part of the metadata. We send it to a collector where we store the metadata. So we'll have a database of certs there, and then we're gonna look at the certificates in that database. We can do that in real time. We can look, once the sensor captures that certificate, we can classify it. But this is not the architecture we're designing. We're designing the other architecture. The sensor sends it to the collector, and then we go to the collector and we look at the certificates in the database. Yes.
So the point is that you have a searchable web UI where you can look at historical alerts related to that came from this classifier.
So the reason I ask is with Lockheed, we've got our own object-based IDS. We do real-time alerting on it. We have our own few machine learning. It's not for certificates yet. It seems like this would be a great fit for that kind of model. Where you're going with it or different things.
I see. Yeah, we can go with it, but I think this is not what we're choosing to do. Yes.
So your malware sample set, do you find that it's difficult to maintain an active enough set of samples where the IOCs you extract from them, their callbacks, are still live by the time you reach out to threat source?
I don't have the details. It was Jason that's doing the work. I would guess that some of them are still not live. I don't know what the ratio is or what the percentage is, or how limited we are by that, but I'm sure it's there. Yes?
What of this is actually available for general use? Like, is any of the data available or the code available?
The code, I can't answer that, sorry. I have to check. But if you can, send me an email, and I will let you know.
Okay, thank you.
No problem. All right, thank you.